As we saw, quantum mechanics actually started from trying to understand how light works. We remember we could not understand the colour and the spectrum of hot bodies, such as light bulbs and the sun. That led Planck to propose the quantization of the emission of light in units of Planck's constant, h, times the frequency of the radiation. Einstein clarified the ideas here by introducing the idea of the photon, saying that in fact light was always quantized in this way. It was always made up out of these particles, which we call photons. Einstein was also able to clarify important relations between the emission and the absorption of light, and to show that, in fact, there had to be two different kinds of emission, so-called spontaneous emission, which is predominantly what we see from the sun and light bulbs, and stimulated emission, which is predominantly what we see from lasers. His argument here was very clever. He made some simple assumptions and required that the whole theory should make sense from the point of view of thermodynamics. This approach is known as Einstein's A and B coefficient argument. This gave some quite correct and rather useful results, while neatly sidestepping the details of just how the interaction of light with matter actually works quantum mechanically. At the time, he had to do this because we did not yet have a good quantum mechanical theory of matter. This work was before Schrödinger's equation and Heisenberg's matrix mechanics. After the Schrödinger and Heisenberg methods opened up our quantum mechanical understanding of matter, others, especially Dirac, then went back and completed the basic theory of the quantum mechanics of light. This gave us a microscopic treatment that was consistent with Einstein's clever approach, but without having to rely on thermodynamic assumptions to make it work. Later on, for example in the 1960s, the theory was further expanded, especially by Roy Glauber and others, to give us the basics of what we now call quantum optics. Having a sound and complete theory became rather important scientifically at that time because of the invention of the laser. The laser turned stimulated emission from a scientific curiosity into an important phenomenon we exploit every day. For example, the long-distance transmission in optical fibers that carries our data over the internet is based entirely on the use of lasers. With light, we are of course quite used to the very successful classical theory of electromagnetism based on Maxwell's equations. We know that this theory explains things like radio waves very well. Light is also electromagnetic radiation, and we can understand many aspects of light quite deeply with those classical theories, including most of the physics of the propagation of light. But when we want to understand how light interacts with matter, we need a good quantum mechanical theory. One of the surprises here is that what we might regard as the most common processes, the simple emission of light by the sun or light bulbs, is the one that forces us to treat light quantum mechanically. This is the process of spontaneous emission. To explain that, we need to understand how to get photons in our theory of light. And that means we have to quantize the radiation field. So let's see how this works. The quantum mechanics of light is in some ways quite different from the quantum mechanics we've done so far. And quantizing the radiation field can sound like a rather challenging and rather exotic prospect. There is, however, a lot of good news here. First of all, we will be able to start from a Schrödinger equation picture to set up our quantum mechanics of light. We will always be able to link back to that picture if we want to. Secondly, in setting up this quantum mechanics of light, we will also set up the quantum mechanics we need for all sorts of simple oscillating systems and for other kinds of waves. Though we won't have time to discuss them in detail here, acoustic waves, that is sound, or vibrations in solids, can also be described in a very similar way. Those waves and the associated quantum mechanical particles, called phonons instead of photons, are very important for understanding many basic effects in materials. The interaction of electrons and phonons is one of the major limiting processes when we try to move electrons through materials. And phonons also describe many of the thermal properties of materials. So this quantum mechanics we're setting up will have many uses, not just for light. Thirdly, as we work through this quantum mechanics of light, we will also be introducing one of the other important ways of writing down quantum mechanics. This approach, which is very elegant and quite simple to use, involves what are called raising or lowering operators, or more exotically, creation and annihilation operators. This notation is so elegant that it is used quite extensively, even when we are not particularly concerned with the subtleties of quantum optics. If you didn't know this notation, you would, of course, be completely lost. You can, however, be sure that this notation is indeed quite easy to use. There is really only one core algebraic manipulation to remember. Despite its simplicity, understanding it and its implications takes you to the next level in quantum mechanics. So let's start our discussion of the quantum mechanics of light. To do this, we look again at the simplest oscillating system we know, the simple harmonic oscillator. Now, you might reasonably point out we've already solved this problem. Was there something wrong with our previous solution? Well, no, there was nothing wrong with it at all. When we solved it, though, we just performed a rather direct solution of a differential equation. Now we're going to write that solution in another way. This new way is particularly elegant mathematically, but it's still exactly equivalent to our previous approach. In this method, we treat the harmonic oscillator using these raising and lowering operators that take us from one harmonic oscillator state to another. This method will work for any simple harmonic oscillator. After this, the key step we will take will be to figure out how to write down the electromagnetic field as a set of such oscillators. Once we do that, the quantization of the electromagnetic field is quite easy. We will already have done all the hard work. And we will find, quite magically, that photons simply appear on the paper in front of us. Now, we may remember from before that we have a Schrödinger equation for our harmonic oscillator in this form. It's the usual energy eigenequation with a Hamiltonian here operating on some wave function equal to an energy here, the eigenenergy, times that wave function. And here explicitly is the form of our Hamiltonian for the harmonic oscillator, a kinetic energy term here for this mass m, minus h bar squared over 2m times d2 by dz squared, and a potential energy term that's proportional to z squared. Explicitly, it's 1/2 m omega squared z squared, and omega is the angular frequency of oscillation of this harmonic oscillator. Now, we can introduce a dimensionless distance, xi, which is the z parameter, the z coordinate, but multiplied by the square root of the mass times omega over h bar. And that will allow us to write the Schrödinger equation somewhat more simply as 1/2 times minus d2 by dxi squared plus xi squared times psi is equal to e over h bar omega times psi. So that's a more compact form here. Now, that form we had just written down, minus d2 by dxi squared plus xi squared, might remind us of a simple algebraic relation that is the difference of two squares of numbers. So in the form we're going to write it here, that would be this relation. Minus a squared plus b squared is equal to minus a plus b times a plus b. And we can easily check that this relation is correct. In the present case, though, we're not just working with numbers, we're working, in this case especially, with an operator. So d2 by dxi squared is an operator. And if we examine a product analogous to this form here, which would be this form down here, we do indeed get what looks like our difference of two squares, but we also get another term. So this term here would be analogous to minus a plus b, this term would be analogous to a plus b, and this term here would be analogous to minus a squared plus b squared, but because we're working with operators, we also get this additional term that we cannot quite throw away. So in this expression then, in addition to having the term we're looking for, that we want to rewrite, we have this second term we cannot simply discard. We note that, however, for any function f of c, if we take this term here and operate on f of c, then we can write that out explicitly. So from our first term here, we end up with d by dc of c times f of c, and we can write out our second term explicitly also. We take the derivative of this product here. That gives us f of c times dc by dc plus c d by dc of f of c. So that's this term written out, and again just repeating this term here. But we notice first of all that these two terms just cancel one another, and we notice also that dc by dc is just 1, so all we're really left with is f of c. Since this relation that we've just derived here is true for any f of c, then we can in general simply write that this expression here is equal to 1. When it's operating in any function, it has the same effect as 1 times that function. So from this expression that we had, we can now substitute using this relation in here, and rearranging slightly then, we have this term is equal to these two terms, and we take this one over to the other side. That becomes plus a half. So we've managed to rewrite our Hamiltonian here as a product of two terms plus a half. This one, 1 over root 2 minus d by dc plus c, and this one, 1 over root 2 d by dc plus c. Now, we can choose to write these terms as raising or creation operators. This one here, that's one of the two terms we were multiplying, and this one's pronounced a dagger, so this symbol here is our dagger. And what we can call a lowering or annihilation operator that we write as a. So we recognize these two terms. These are the two terms that we multiplied together in our expression for the Hamiltonian. And these operators, incidentally, are Hermitian adjoints of one another. We've written them that way because this dagger means that we're taking the Hermitian adjoint. But in general, we can also show explicitly that these two terms are Hermitian adjoints. This operator d by dc, we may remember, is what we could call an anti-Hermitian operator. We originally showed that just for this spatial derivative operator. So if we take this expression here, when we take the Hermitian adjoint of it, which is the same as a complex conjugate in the end, because this is a number, we get a minus sign here. But C as an operator is Hermitian. So if we take the Hermitian adjoint of everything here, the C will go to C, and the d by dc will go to minus d by dc. Therefore, we can see that A and A dagger are indeed Hermitian adjoints. That is, formally writing that out, this term here with phi A psi will be equal to the complex conjugate of psi A dagger phi here. But note that neither of these operators is itself Hermitian. It is not true that A is equal to A dagger. These are not Hermitian operators. Now, from this expression that we've just written out, and using these definitions of these two operators, of course, we can rewrite this Schrödinger equation now rather simply. It becomes A dagger A plus a half times psi is equal to E over h bar omega times psi. So we can, if we want, rewrite the Hamiltonian in this form. We can take the h bar omega over to this side, and we have the Hamiltonian is h bar omega times A dagger A plus a half, which is a very compact form. We know from our previous harmonic oscillator solution that the eigenenergy for the eigenstate psi n is of course just n plus a half times h bar omega. So, given that the Hamiltonian is h bar omega times a dagger a plus a half, then we know that mathematically the following statement is true. A dagger a operating on psi n must give us n times psi n. So this entity here is a rather interesting operator in its own right. This is the number operator. Since, as we said, a dagger a operating on psi n is equal to n times psi n, this operator a dagger a obviously has the harmonic oscillator states as its eigenstates, and the number n of the state as its eigenvalue. So it is sometimes called, as we said, the number operator. So we can write that as a capital N with the operator hat on it being equivalent to a dagger a. And this has the eigenequation that n operating on psi n gives you little n times psi n.